at the bottom sort of the Hadoop stack is the Hadoop distributed file system. And this sort of goes back to that assumption where I highlighted in the beginning, is we need to get over the idea that you can store data on a single machine. So what the Hadoop distributed file system does is it takes all of these various different sources of input data, whether it be databases, scientific data, user data, system-generated data, and it breaks this data into small pieces, and it distributes them all over a network of commodity machines. Each of these machines is roughly identical. They are all anonymous. None of them have a meaningful identity beyond the fact that they are capable of storing blocks of data. And then files are broken into blocks, and they're distributed across all of the servers, and that replication protects the data from hardware failure. So we don't use systems like RAID. We expect the hardware to fail. And in expecting the hardware to fail, the software system will take every chunk of data and replicate that across multiple machines. And there's two reasons to do this. The first one is obvious from a fault tolerance perspective. When a machine blows up, you want to make sure that that data still exists somewhere. But the other reason is that the more you replicate your data, the more accessible that data is. If there are more copies of that data across your network, there are more people that can access and use that data simultaneously. So the next thing I'm going to talk is about MapReduce. And the important thing to know about MapReduce is it leverages data locality. So let's look back at these same commodity machines we have here. They all look the same. They all don't have any identities. They've all got various chunks of data now about our data set distributed over each one of them. The old way of doing this, so to speak, would be to, you have a SAN on one side of the room, which has got your network attached storage, and maybe it's a filer or whatever. Maybe it stores, 20 terabytes. And then on the other side of the room, you've got a blade center, which has got lots of CPU in it. And then in between them, you've got the best network connection you can get, a 10 gigabit connection. I will let you guys do the math yourself, but transferring 50 terabytes of data over 10 gigabits still takes a really, really long time. If you mess anything up in your computation, you probably have to start over. So what the MapReduce programming model does is it acknowledges the fact that the data has already been distributed across all of the machines. And rather than try and pull the data to the computation, it pushes the computation out to the data. Because your code, your computation is bytes. Like, it's not a lot. Maybe it's some Java bytecode. Maybe it's a C++ binary. Maybe it's a whole 100 megabytes of object code. That's still trivial in comparison to the size of data that we're working with here. So you just sort of like take this model and you flip it upside down and say, OK, I'm going to push the computation now out to the data. So what's going to happen now is each one of these machines is going to process that little chunk of data that it has for your data set that's relevant to your question. And then it will go and it will, rather than, there's this map phase in the word MapReduce, and the map phase is where you scan over all of your data and you sort of extract the interesting data that you want to use to answer your question. And then the reduce phase is where you aggregate all of that data together so you can actually drill in on the answer. And then the reduce, basically, the data that goes across the network between the map and the reduce is the only real load that you induce on your network. So if you're asking a simple question, which is primarily scanning through data and extracting the 1% that you're interested in, yeah, you'll move 1% of the data across the network, which is very different than pulling all of that data across the network to then decide that you don't want to use 99% of it. So the key things that you need to understand are that the data elements are processed locally in parallel, and that reliable computation is managed implicitly by Hadoop. So at any point in time, one of those machines can fail. It just happens. But because machines don't have identities, and because we expected that machine to fail, we can just restart that computation on one of the other two machines that we know has the data that we care about on. And rather than moving any data around, we just take that computation now and we push that over to one of those new machines. So the last thing that I want to talk about sort of in the technical overview is reliability and fault tolerance and how we achieve this with software. At any given point, one of these machines can fail. It happens. It will happen every day in a large cluster. Maybe the whole machine won't fail. Maybe just one hard drive will fail. Hadoop was designed with this in mind from the beginning. So when this machine fails, data and computation are both implicitly rebalanced in a way that's completely transparent to you as an end user. So what does this mean? When your data nodes, your slave workers in your cluster fail, no one's pager goes off. What happens is, at the end of the week, you get a list and say, hey, these 17 machines are broken. Go fix them. So you pull those 17 machines out of your network. You probably have 17 over here, waiting to slip back in. You put those 17 new ones in. They are similarly anonymous as they were before. You send the first ones off to repair. And then next week, when 17 different machines are broken, you take those ones that were live 2 weeks ago, you put them back in. They have completely new anonymous identities. They have no connection to who they used to be or what they used to do. But they continue to participate in this data-intensive cluster to allow you to store and process these huge volumes of data. So to take away here, data loss is prevented through automatic replication and rebalancing, and computation is restarted automatically and, most importantly, without any user intervention. If you have a bunch of pizza boxes ready to go that know how to network boot, you can set this up so they just assimilate. Zero actual configuration on the master. What happens is if a slave reports to the master and says, hey, I'm ready to go, the master will start provisioning work to it, start balancing data onto it. You don't have to do anything. The dirty little secret I've been keeping under the table for this whole thing is that there is actually, one machine does actually have an identity, and it is the master. And sometimes it does fail. But now we can actually go back to the fact that the master is actually just one machine. So it probably only fails once every 2 to 4 years. So it's very common to buy a very beefy, highly reliable machine for your master and buy cheap, unreliable commodity machines for your slaves. And then what you can do is there are some methods. This is something that one of the most common things we help our support customers with is getting high availability out of your master. And there are ways to do this. But for example, like if you have a system that assumes one master and you want to have a hot standby, what if there's a network split? And all of a sudden half your machines can't see the master, and half of them think this one's the master and that one's the master. It goes south really quickly. So this is something that, yes, is doable. The project sort of out of the box doesn't support this, but that's why Cloudera exists, is so when people really have these production requirements that we can help you through that.